Welcome, everyone, to tonight's special evening lecture in which we extend the warmest welcome to Assistant Professor Lola Ben-Alon, who, as of this semester, is, I'm delighted to say, joining us as a full-time faculty. Lola was selected after a year-long search, and we're so happy to have her join the school to rethink our approach to the questions of technology in architecture and in buildings, in service of radically redirecting our ideas about where we are and where we need to go in light of the urgency of the environmental crisis the planet is facing. Although we continue to list the statistics we are now all familiar with in terms of how much the building sector contributes to the total global carbon emission every year, that knowing that we need to reduce emissions by 50 to 65% by 2030 and completely phase out fossil fuel CO2 emissions by 2040, if we are to ensure a 67% chance of limiting the average global temperature rise to 1.5 degrees Celsius above pre-industrial levels, according to the most recent 2018 IPCC special report on global warming of 1.5 degrees, it still seems that the pace and Western mode of urbanization that continues to spread and be adopted around the planet, together with an all too often uncritical embrace of new technologies, stands against some of the progress being made in other domains of building and building practice. For Ben-Alon, this challenge is multifaceted and can only be engaged as such. At the intersection of social, material, and economic concerns and practices, Ben-Alon's research refutes accepted notions of technological progress and instead proposes new modes of hybridizing old and new, north and south, east and west, local and global, as a means of fundamentally altering how we think of building in the world today. For Ben-Alon, the materials of the future are those such as earth and mud, computing their strength to compete with and one day replace concrete and other unsustainable materials. She sees cutting-edge building construction as an opportunity to rethink labor practices and empower women and vulnerable populations to build their own structure. In Ben-Alon's view, embodied energy is considered as crucial to architects as their and their clients' economic calculations. This commitment to hybridizing and hybridity is transposed from Ben-Alon's research to her own education and multifaceted interests and talents. Ben-Alon is an engineer, a researcher and scholar, as well as a curator, designer, and committed collaborator. As a postdoctoral fellow and adjunct faculty member at the School of Architecture at Carnegie Mellon University, she taught numerous courses leading technology in the school there. Her research focused on life cycle assessment, perception surveys, and building policy development to reinsert earthen construction assemblies such as light straw clay, rammed earth, and cob into the mainstream construction industry. She earned her BS in structural engineering and MS in construction management from the Civil and Environmental Engineering program at the Technion, Israel Institute of Technology. Parallel to her engineering background, Lola earned a diploma in critical and curatorial studies at the Technion, where she co-founded Art Espionage, the experimental art and architecture lab. She has exhibited various interactive urban interventions, public art and performance art in museums and galleries around the world, including the Shanghai Biennale Gallery and Tel Aviv Art Museum. She also served as a curator and content developer at the Madatech, Israel National Museum of Science, Technology, and Space. Lola is passionate about fostering connections between academia and community by promoting social engagement in the production of the built environment. She's the academic advisor to the Terra Collaborative, an all-women organization that provides hands-on natural building training for women and youth in developing communities. Through sharing skills and knowledge that promote healthy and affordable living environments, Lola hopes to diversify the building industry and catalyze new intersections and creative dialogues among the various disciplines of architecture, engineering, art, and sociology. Please join me in welcoming Lola Ben-Alon, together with Lucia Ale, who is also teaching for the first time this semester at GSAPP and who we are so thrilled to count amongst our faculty. And she will be giving the response this evening. Welcome, Lola Ben-Alon.
Thank you so much, Amal. Let me share my screen. Thank you so much for the warm welcome, Amal. I'm so delighted to give this talk today and to be joining the school. And I will start today with a little bit about myself, although Amal did such a sensitive and wonderful job as always to know and become engaged in what the school faculty is doing. So indeed, as Amal mentioned, since the beginning of my engineering studies, I was really fascinated with non-conventional building materials. And in this photo, you can see me at the engineers building competition that tests students' degree to use structures that are efficient in terms of their strength to weight ratio. And in my structure, I incorporated materials from the aviary industry and that are known for their really good strength to weight ratio. And not only that I won this competition, but I was also the first woman to achieve this award. And we'll go back to this point of diversifying the building industry at the end of my presentation today. So parallel of to my engineering education, I really became passionate about user interaction and the mechanisms behind our everyday commons. I co-founded the Experimental Art and Architecture Lab at the Technion in Israel, where we developed and exhibited really critical projects in public venues, museums and galleries in Israel and around the world. And this project is called Earth, or in Hebrew it's Eretz, or in Chinese 2D. And it is a trilogy of installations that question the role of the artist and the art trade in a global area, and specifically the mechanisms behind sourcing art from different locations. And as part of this project, we traveled and documented artists in Yiwu, China's international trade city, where 70% of the world's paintings are made today. And we traced the path of art production by sending 1,000 photographies of Israeli landscape to those factories, sweatshops, namely in China. Most importantly, this work was about calling to question the socio-cultural implications of consuming art that goes through a supply chain in which the actual artist is anonymized and de-identified. We wanted to bring the sweatshop artists to the forefront, and this is the opening in Shanghai, where we celebrated the artists' artwork who were present there with their families. So in my current work, I use these perspectives to inform my research and teaching, merging these broad interests of building construction, new materials, supply chain mechanisms, and critical thinking. And what I already knew, as well as you know, is that although each of these building materials were initially taken from earth, fiberglass comes from sand, construction steel from ore-bearing rocks, and concrete from limestone, they had to go through these complex processes to become the building products we know of. And the problem is, as Amal mentioned, is that we have been increasing the amount of processing and transportation between harvesting something at source and placing it into our buildings. And that results in a staggering environmental deterioration and impact of 15% of global climate change, 20% of global energy use, and up to 40% of global solid waste that is due to making and processing that is required for our conventional buildings. And what keeps the building industry behind at business as usual is not necessarily lack of data, but there's a plethora of data out there, but it is how data is presented. So as a postdoc at Carnegie Mellon Center for Building Performance and Diagnostics, I aim to recapture the share of the building sector. And you can see here how, according to EPA, the building sector accounts for 13% of greenhouse gas emissions. But if we allocate the building share from the electric power sector, which is not an end-use sector, we get 32% for building. And by extracting the portion of building materials, the embodied emissions from the industry sector, we now see that building account for 38% of emissions. And this is really important because these figures, these numbers eventually affect funding and resources for decision-making. So many investments are located here in making improvements into energy generation, into electrification. But these are very, very costly investments and developments. And what we should really do is reduce the energy that is consumed in the first place. So when we look closer, we can see that the more profitable avenues are in here in investing in the built environment. And specifically, my work is motivated by the repeating and accumulating impacts that are dictated by the building envelope and its properties. So my point of departure is in building envelopes that use natural and living building materials. And these types of materials are defined as readily available, minimally processed, non-toxic materials that are community engaging, namely farm to building. And specifically, the combination of earthen and bio-based materials include fibers as a tensile strength provider, sand or aggregate as a compressive strength provider, and clay as the magical binder. And the various combinations of these materials, of these raw materials, produce a diversity of styles and techniques. And of these various techniques, I will focus today on cob, rammed earth, and light straw clay due to their broad range of styles and thermal possibilities. So cob is a monolithic sculptural technique. Rammed earth uses formwork and mimics the process of sedimentary rock creation. And light straw clay that is an insulative infill tamped within a structural frame. And these materials are indeed very, very sustainable, offering a waste-free life cycle, as we will review later on. They're also very healthy for occupants. They're non-toxic for construction workers and tenants, and they were shown to act as passive removal materials for VOCs that as you can see here in this chart. They have high thermal inertia and high grade capacity, which make them act as a flywheel of indoor relative humidity. So they were shown to provide relative humidity levels that are optimal for human health. Their permeability makes them a good autoregulator, and their mass results in quieter spaces, and they buffer electromagnetic fields, which is an increasingly important feature, especially in urban setting. And while it seems totally out of our focus, Earth still shelters 3 billion people around the planet, and it is a vernacular building material in Europe as it is in Africa. Therefore, this material that has been proven itself for a millennia should be enhanced rather than replaced by industrialized practices. Earthen materials also promote community engagement where everyone can participate, including kids and elders. And lastly, earth is all around us and just underneath our feet and can be used from the foundation excavation of a building project. So it can be dirt cheap. So just as you are what you eat rings true and have generated an immense industry of healthy foods, so does the spaces we live and work in affect our life and health. And the trend of having healthier and low carbon materials will only increase in the next few years. It is therefore our responsibility to make sure this growth is made sustainably. So as part of this growth, our challenge is to ensure that as building professionals, we vote first of all vote, and also we vote with our design decision making. So the growth of building materials need to follow responsible growing practices, very similarly to how permaculture and sustainable farming for food. So to ensure a sustainable catalysis of an industry, we need to investigate how to properly integrate natural building materials into the mainstream construction. We first need to address a technical gap due to scattered data to ensure we have adequate performance data for different climates, right? We also need to address a perceptual gap that I will show you later on. And there's also a major regulatory gap where emissions from building code make it harder to achieve a building permit to projects like low-income housing. And field and professional development in turn is pushed back. And lastly, with lack of professional development, earthen building practices really remain in a traditional niche, holding back innovation. My work tackles each of these gaps, and we will review some of the key findings, starting from the perceptual gap. So one of my major projects started with this perception survey, global perception survey that asked what people really think about earthen buildings. What is the problem? Why isn't it mainstream? And what was astonishing to see is the strength of the perceptual barrier. So 25% of respondents who were earthen building experts, including architects, engineers, builders, etc., from 12 different countries, mentioned the perceptual gap in the form of cultural prejudice and social perception. So how do we overcome this negative perception? We use appropriate design and testing protocols. Earthen materials are perceived as low-tech, but they can act as a high-tech material. Appropriate design of earthen structures should include, first and foremost, a good pair of boots, a high footing, and an umbrella, a deep roof hang to reduce rain-driven and water erosion. And there's also the perceived limited building height. But actually, earthen infills and clay-based interior finishes can be applied in any scale. And these options are developing in places like Germany and New Zealand, where great earthen building codes exist. So now that we know more or less how to change perception, we need to enumerate, to prove the environmental urgency of natural materials to influence building policy. And I'm an engineer, so I'm going to give here some technical slides, so bear with me. And before we dive into these few technical slides, I would like to emphasize that building science and technology, very similar to engineering, can be a very technical field, and therefore we need to form ethical principles to choose what direction we are going. We need to ensure we draw on our knowledge and skills to address social problems and to shape building policy. So one of the main goals of this project that I'm going to show now was to use life cycle assessment, LCA, to form environmental product declarations that could eventually influence building codes. But beyond the environmental impacts, it is really how to address how energy demand and climate change affects societal impacts like access to materials and circular economy. So when using environmental life cycle assessment, LCA, it is very important to provide a comparison so that the results of the research could then influence policy and decision-making. So in my LCA, I compared between earthen assemblies, light straw, clay, cob, and rammed earth, and conventional assemblies, wood and concrete masonry. It is also very important to choose the right impact factors and to show the aggregated inventories and their circularity effect. And when I say impact, I refer to how the various substances from the life cycle inventory, the coal, crude oil, the different emissions are then factored and summed up to give energy demand, climate change, human health, all these impacts that are then very meaningful for policymakers. Now, there are many life cycle studies out there for conventional assemblies, but not for earthen, and therefore a life cycle inventory for the earthen assemblies was needed. And the way to pursue that was by accounting for each of the constituent materials. So for instance, for straw, the inventory includes the various processes from field preparation to crop maturity, including infrastructure, equipment, fertilizing, pesticides, all of this comes into the system. And lastly, another important aspect was to not only examine the embodied impacts that are very important, but kind of obvious for earthen buildings, because of course it's very low, but there are lower impacts, but to also, we need to test the trade-offs between embodied and operational impacts over the entire life cycle of a building. So each wall was then thermally modeled for 6 different climates to analyze the cooling and heating energy demand in buildings with these different wall assemblies. And this is a visual summary of the impact assessment results of the embodied phase. And as predicted, the embodied impacts of the earthen assemblies on the left here are indeed much lower from the conventional wood and CMU assemblies. And when further analyzing the sensitivity of these results, even the worst case scenario, you can see here the error bar for earthen assemblies is still much better than the conventional assemblies. And what really makes a difference for earthen materials is to really optimize mixtures to decrease wall thickness and to develop test procedures to increase the use of local soil. So this is where we should focus if we want to innovate these kind of materials. And this is a final summary of the aggregated embodied and operational impacts, including maintenance over a 50-year lifespan for 6 different climates in the US. And significantly, the embodied performance of earthen assemblies is so much lower, so much better, lower is better in terms of environmental impacts, that it offsets the operational heating and cooling values, even in climates where uninsulated earthen mass doesn't perform that well. So just to illustrate, we get up to 53% energy reductions when replacing synthetic insulation with light straw clay infill, which is both a mass and insulation. So it's kind of a super assembly, which was proven to outperform all other assemblies, by the way. These results are even more dramatic for emissions because emissions result from energy generation, but also from chemical reactions during material processing and fugitive emissions during quarry operations. So overall, in terms of emissions, we get up to 80% climate change impact reduction for earthen assemblies as opposed to conventional assemblies. And I promise this is one of the last technical slides, and we now get to the main takeaways of this study. So first, energy codes should really account for more than operational approaches. It is not only about adding a good layer of insulation with an R30. It's also about how that insulation was produced, how it is demolished, how toxic it is at the end of life. Second, we should diversify uniform and insulation-driven energy requirements to capture mass and hygrothermal benefits. In fact, current research suggests that thermal pleasure, also known as thermal alliesthesia, arises from dynamic and radiant environments that can be passively generated by earthen walls. And lastly, we need to include earthen and fiber-based materials and assemblies in building codes rather than extracting these materials from traditional practices. And these points lead me to my policy analysis and work on promoting building codes. So when developing a new building code, the opportunity is in starting with a blank page to mitigate unnecessary complexity that is already existing in codes. But the challenge, however, is in using existing precedents to avoid reinventing the wheel. And this is just one example of how policy analysis looks like, where we compare different earth and building codes from around the world to draw from the benefits of each document in terms of seismic provisions, LCA incentives, ease of use, etc. And as part of this work, an important collaboration with the Cobb Research Institute was formed, and eventually a Cobb construction appendix was approved at the International Building Code and will be included in the 2021 IRC Model Code. And I think this is a great example to how we can form really good collaborations between academia and the field to catalyze an actual building policy change. So just to explain, the meaning of a building code like this approved is twicefold. In the US, it means that people and companies who are struggling with approving structures using this material, this earthen material, will no longer struggle. They have a building code, but also countries that are looking up to the International Code Council and its documents will be able to adopt the Cobb code rather than extracting that traditional practice from their region. They could justify that building practice with this code. The next phase is to expand the boundaries of what is possible through design innovation and digital pathways, and to make these materials more accessible. One of the questions are, how do we contemporize the vernacular? How do we improve assemblies like rammed earth that are very exciting, but are often very limited to linear surfaces? So this project asks questions like, why are we changing form? Why should a plain wall not be okay? So rammed earth is so beneficial for hot climates. We wanted to investigate possible self-shading and self-cooling by geometrical variation. Using a solar analysis, we developed surfaces that increase self-shading by 40%. And then we used these retraced surfaces and developed adaptable formwork that allow new surface tectonics for rammed earth. So while using unbaked raw soils, we achieved geometrical variability, different combinations, and exciting new avenues for clay-based self-cooling wall assemblies. We also need to navigate the unique challenges of working with a material that has been moved, mixed, and contaminated for centuries. So in this other study, we mapped local Pittsburgh soils, and as you probably know, Pittsburgh is a very strong industrial city. So indeed, with soils that are very contaminated, and we conducted chemical and structural lab tests and employed then digital processes of robotic manufacturing. And eventually, through a heavily hands-on process, we aimed to really empower and unite different communities around the city through a participatory exhibition in Carnegie Mellon Art Gallery. And our team that helped put up the exhibition, as you can see here, all fell in love with the materials, of course, after working and feeling the material. Because eventually it is really about hands-on working with these materials to gain, to be empowered with this self-sufficiency. In this project, you can see me applying a final sculptural coat from Cobb to a shower that is made from adobe bricks. So I gained over 1,000 hands-on earthen construction practice throughout my studies. And this is, by the way, the shower that is here finished with a layer of white tadalact, which is a burnished lime plaster and a tile mosaic. And it is stunningly located in the heart of Rancho Mastatal, Sustainability Educational Center in Costa Rica, which serves as a living lab for natural building materials. So you can go there and really experiment with the wackiest structures and make really beautiful things. So using the right clay mixture can result in a super strong, unfired plastic matter. The use can be from large scale walls, partitions and prefabricated walls to bricks, small scale furniture and artwork. And this is, for instance, a technique that uses clay with weaved chopped fibers for sculpting, rather than the usual pottery clay that can be very brittle if it's not fired. And there are very few artists who are familiar with this technique. So we need to conserve these traditional trades while also incorporating new modes of material thinking, which is why I taught Earth to architects and engineers in Carnegie Mellon. This course is called Down to Earth, and it had a lot about work about process. We ask, what does a material want to be? And how do you change your design based on the material behavior? We design and built with natural materials while collaborating with Pittsburgh's local farming collaborative, Grow Pittsburgh. And in a hands-on building workshop, we brought together students, community members, and urban farmers. Students also designed environments in response to alternative modes of engagement and off-grid resiliency in a desert climate scenario. And this was informed by the local availability of materials like clay-rich soils, desert silt, gravel, limestone, reed. And students really asked themselves, how do they account for systematic flows of materials, climate, culture, and food as they identified opportunities for intervention? So my work catalyzes the broader adoption of earth and natural fiber materials, and there are many other exciting building materials that require similar analysis. I call these the next generation of building materials, and they all require additional environmental, thermal, perceptual, policy, design innovation, and educational avenues to be implemented in mainstream construction. And this avenue, this thing about materials has a whole bunch of research projects that I'm currently conducting. But it's not only about materials. In addition to materials, the next generation of building science and building technology systems include systems and processes that also need to be justified, catalyzed, and implemented. And the basics is really about understanding how environmental, structural assemblies and infrastructure systems work together. But it's more than that. It's how we catalyze greater connection with our environment through biophilia, the love of life, how we develop a life cycle thinking to account for the supply chains and societal impacts of our design decision-making, and how do we use technology systems to bridge between communities, to grow food in our buildings, and to provide off-grid resiliency. And this is a good opportunity to shout out to our GSAPP students that are listening to join me in my outreach ventures. So I invite you to actively engage and contribute to different venues, from the Terra Collaborative, which is an all-women organization that provides hands-on natural building training to women and girls that then become building training providers to their own communities. And this is led by Liz Jondro, but also to research collaborations and to influencing the scientific community. We need to act both bottom up and top down. Yeah, thank you so much for having me. Lucia, would you like to engage in a conversation now?
be happy to. Hi, Lola. Thank you. I'm going to now look at this camera, but I will also direct my eyes up here where I have some images and I have eventually the questions. So forgive my my wandering eyes, I should say. Thanks so much, Lola, for the presentation. I took to heart Dean Andraus's instructions, which were not only to come, have a conversation with you, but also just now to say that we have to radically redirect where we are and where we need to go. So just to be clear that the stakes are, that low. So just, I'll speak to the audience first, and then maybe I'll ask you 3 questions. So, not too long ago, as maybe as recently as the last decade of the last century, it was still possible to say that engineers are those who do the calculations for architects. And both sides of this collaborative picture would have found pride in that statement. The architects would perhaps have been proud that they design structures that require calculation, maybe intense calculation. Maybe this would have been a sign of heroic form or of structural bravura, perhaps formal complexity. There was a kind of thrill to calculation. And the engineer would have perhaps found a certain amount of pleasure in knowing more than the architect, in opening and pushing the possibilities of efficiency and performance, perhaps some structural expressionism. And indeed, by the end of the last millennium, by which I mean the year 2000, it seemed like the culture industry had begun to recruit its star architects, even among the structural and civil engineers. So things have thankfully changed, and I think Lola, Ben-Alon, and a number of other young engineers are here to show us how much they've changed and how much they continue to have to change. One of the things that I admire about Lola's work is that it shows how much more expansive our conception of calculation has to be, and also how much more expansive the notion of collaboration has to be in order for the kind of radical redirection that Dean Andraus was, and many others have been asking for. So Lola's particular subject matter tonight was materials. And here too, she's been very iconoclastic. In her presentation, she challenged the ultimate modernist myth of materiality, the myth that materials are homogeneous, that they are one thing. That myth took the model of stone and wood as a model for all materials, 2 materials that grow out of the earth that have to kind of be extracted from it. And from which we get the myth that materials are either natural or they're not, that they're either permanent or they're not, that once they're in a building, they stay there forever. And this myth also grew, along with modernism, with an old organicist analogy between human progress and natural growth, and so-called natural growth. Think of what you've heard tonight. You've heard Lola say, first of all, that there are many ways to categorize how exactly materials relate to the earth, and that several of those qualify as natural. And you've heard that embodiment is only one phase in the life of the transformation from natural to cultural. The modernists would have sort of rolled, I hope they're rolling over in their grave now. It's not all embodiment. Some of it is embodiment. Other performances are better described in a different way. And that overall, we have to think past ourselves and past our own architectural timelines, past our own human life timelines in order to understand how materials perform on the earth. Although I was very happy to hear that we can still talk about buildings as having a good pair of boots and an umbrella. I thought that was still useful when you can. So Lola has shown us that the radical expansion of material processing, the intensification of the amount of times we process the earth, the production of carbon, the building sector has meant that we have to calculate our architectural presence on the earth differently. We have to engage in what some historians have called statistical thinking. We can't just calculate the size and the shape of our buildings. As Lola has said, the problem is not a lack of data, it's about how data is presented. And indeed, I hear in Lola's work echoes of the work of scholars in science and technology studies who tell us that the environment itself, the built environment itself, is a kind of visualization of data. The built environment, when we design buildings, we in a way are visualizing how humanity is inhabiting the earth. And according to this view, what we do as architects is create documents of the Anthropocene, not just embodying the Anthropocene, but also making them visual. And so, and I should add, although she hasn't talked very much about this today, but what's especially remarkable is that Lola comes in part from the world of BIM, building information modeling, which is to say she actually knows basically how to manage a building site, which is not something that most architects know how to do, let alone me. But more to the point about our discussion tonight, this allows her to have familiarity with how to quantitatively model social processes. The building trades are just as good of a place to get a picture of how social homogeneity works, or heterogeneity, as anywhere else. And you know you're in the presence of someone who has an abile engineering mind when research that begins in modeling the data about the construction industry yields research about how to rethink materials. So having said all this, I hope I haven't said anything that's technically wrong. But just to get us going, I thought I would ask you 3 questions. The first is about carbon, the second is about the social, and the third is about nature, broadly speaking. My first question is about carbon. And I want to ask about carbon because it's the element that is our kind of interface with the atmosphere, and you haven't really discussed it, although I imagine that some of your slides would have good comparative trades. And I'm particularly well-versed, or I'm best versed, I suppose, in the carbon emissions that are involved in concrete. And I noticed in your slide of how to flatten the curve, the substitution of clinker and ash. That's a big deal for concrete production because it means that you produce fewer emissions. Now, when I'm using a replacement material, let's say I'm using earth instead of rammed earth instead of concrete, I'm producing less concrete, less carbon, but I'm also sinking less of it. I'm also capturing less of it. And I know that in concrete, but also in wood construction, there's quite a bit of debate about how you calculate that. Do we take the lifetime of one tree? Do we say, would it be better to leave a tree to capture the carbon or to cut it off and have that piece of wood basically maintained in the form of a building in order for it to contain its carbon? So I wonder if you could just help us out and talk to us about carbon accounting and whether it's something that in your particular type of earth and material helps.
Sure.
Should I maybe pass it on to you and then ask the next one later? Maybe get you to talk a little bit?
Yeah, of course. I'm happy to answer this inquiry about carbon, but I first want to mention that when we say climate change, we're not talking only about carbon, and although it is the main contributor, it's a wide range of emissions that contribute to climate change, which is eventually the impact factor that we want to look at, because this is the impact that is affecting us as society eventually.
Okay.
So it's again going back to, and it's really important for me to emphasize this, because part of the problem in the scientific community is that sometimes we stop at the inventory level, at the carbon or at the gas, but we need to turn these to impact so we can really, communicate the problem well. And going back to carbon, yeah, carbon sequestration is a really important thing. And the real main difference between fibers and wood is that the cycle of fibers is much shorter. So the sequestration is much more greater and efficient. So using fiber-based or bio-based materials in the form of hemp, straw, stalks of sunflowers are all really very strong, viable materials for carbon sequestration. And you're right, when you compare rammed earth, that is one of the only techniques that you do not use fibers, although there are studies, and some of which that I'm very interested in, to test fibers within rammed earth. Other types of clay-based materials will always use fibers because it's kind of the internal reinforcement that is weaved throughout the material, those fibers. And the carbon sequestration that is associated with fibers is something that adds up to the benefits, the environmental benefits of earth. So when I say earth-based materials, it's a little mistaken because it's always a combination of earth, clay, and fiber-based materials. There will be, sometimes you will use the raw soil as it is. There are ways to test the soil to know how much clay you have in it. And that soil could be perfect for construction, straight off from your construction site, from your foundation excavation. And sometimes you need to add some sand. And then you add the fibers. So this is how you will use the materials. I also wanted to note about the extent to what natural material is. There are I have some colleagues that argue that when you go into an urban context, recycled materials are natural materials because they're readily available, they're minimally processed, they're community engaging, and hopefully, and most of them are non-toxic, or some of them are non-toxic. So they can be also used. And so you see these natural buildings with all these recycled glass bottles and other type of recycled post-consumer materials in urban contexts.
Great, thank you for that. That's what that answers my questions perfectly. That the life cycle of the fibrous material is where sort of that's insofar as carbon sequestration comes into it. It's a much faster cycle. That's great. You kind of already pointed to my second question, which was about the social. And as history theory people, we like to think of the social as this kind of category that was invented and made almost magically homogeneous. And it's taken us years to undermine this. So what I really want to ask you is, what have you learned from your interactions or from your research on perception that you then can apply in your work towards code? And so the longer version of the question is this, that I find your work on the perception gap fascinating. And again, your ability to quantify that is really helpful. And I ask because it seems to me that there's quite a bit of debate about the uses of awareness and of knowledge in the Anthropocene more generally. Historically, you could say the 1970s are supposed to be the moment where ecological awareness arose, and thus we for sure, more knowledge circulated and people became more aware. But the assumption that this would necessarily lead to action and to a redirection, the kind of redirection that, again, Dean Andreas was asking for, has just not followed through. And so there's several theories about that. Some say essentially it's a power relation. There are many people who have knowledge and who have the power to suppress it. Others say that there is knowledge that doesn't necessarily it's too dry, essentially. And there's also maybe an argument to be made for the fact that people are different people when they hear something, and then when they're maybe the person in charge of a construction company having to make a decision about code. So I wonder if you think about that. When you teach your students and when you do an exhibition, you are imparting knowledge and imparting awareness, but then when you go to make an argument for code, awareness itself won't be enough or something like that. That would be the question.
It's a really, really interesting point, Lucia. So actually, I didn't show almost anything from my perception survey analysis because it was too technical, and sometimes it's so into the weeds, and I was afraid to lose the audience. But I gained responses from people who live in earthen structures around the world, as well as professionals, building professionals like us, and builders, architects, engineers who deal mainly with earthen construction. And we think we have a global community and global connections, but that is in part not true, because there are so many cool things that are happening in Brazil and in Africa and in New Zealand that only by reaching out to the people and asking, how do you feel in your home? Is it comfortable? Do you turn on the heating or not? Is Mass really that cold in your climate, or is it like fun is it comfortable? It was really awesome to get all these answers and insights about comfort and perceived comfort of occupants in earthen structures. And most of all, it was really interesting to see the results of the experts and who indicated, this code, this is the problem in this code. That code here, this section has this problem. From 60, 70 experts around the world who are using building codes. So that was really astonishing and really informed the code analysis then. So it was directly related to the code analysis. And I think that in teaching, and if taking this to teaching, one of the main missions is to bring awareness through the hands to building professionals from the beginning of their education. So eventually, permit officials, building professionals, and permit officials who are not familiar with these kind of materials, that will make it harder to, push this direction forward. So it is really about bringing it into educational stage.
That's great. I had a third question, which was about nature, but you somewhat answered it already when you said that some colleagues consider recycled materials to be natural. I was just, I just noticed that you're very careful, very ginger with your use of the word nature, natural, that you don't avoid it. But on the other hand, essentially are talking very much about a social sphere. They're mainstream materials. You're really taking into account the mainstream. And so I just wondered if you have any specific words for architects. What is our relationship to the mainstream? Because on the one hand, you're definitely talking about pushing the envelope, doing experiments, talking about innovation, what allows it, what doesn't allow it, and bringing new knowledge into the fore. On the other hand, we want to be mindful of the role that mainstreamization or that rendering things generic plays in the pushing forward of environmental goals. So I don't know if you have any particular words of wisdom on that. And then after that, I think I'll take the audience questions.
Sure. I think that when I say integrating into mainstream construction, what I'm actually trying to say is that the grassroots that is currently there, the DIY house movement, the make it yourself cob is really important. I personally love it. I, participated in various workshops to learn how to build with these materials. But this is not how these materials could benefit the larger society, in terms of, providing these health benefits to different layers in our society.
Right. Okay, so speaking of layers, we have, I think we can take maybe 3 or 4 questions. I'll start with one that's quite straightforward. It's from an anonymous attendee who says, I tend to see earthen and fibrous materials used in hot climates. Do you see any differences or challenges in approaches to natural materials in cooler climates?
This is a wonderful question, anonymous attendee. This is a really an important point of perception. So earthen materials are historically used in hot, arid climates, but also in places like England that are marine and colder. And it's really acting different than what we know of insulation and how building codes dictate today the way we build. It's just a different system of how it operates, how it links our indoors with our outdoors. It's not insulating our indoors from our outdoor. It just links it differently by storing energy, absorbing solar energy, for instance, and then releasing it over a cold night. So earthen materials can viably be used in cold climates. However, I will never use an external earthen envelope in places like Maine or New York, because in cold winter, they will just leak, they will store that indoor energy and leak it outside. But what I will do, I will incorporate earthen assemblies within the insulated envelope, so that, especially assemblies that could then be exposed to solar direct gains, or wrapping any heating system. There are many cool projects of rocket stoves that are covered with cob that then provide heat throughout the night. You turn off the stove and that battery keeps on working. So it's a viable material, but there is a way to use that material in cold climates. So it's a really good point. Thank you.
Okay, thank you. We have Angel Castillo who asked a hypothetical question. I have the opportunity to build and design a home. I hope Angel does have one day the opportunity to design a home. How would I get started with using these materials, these building methods, from technical design and process to finding someone to consult or teach with?
Yeah. So this is a great time to maybe mention the Build Well source, which is currently an initiative. I'm working with some folks. It is led by Bruce King, who is a wonderful, wonderful engineer from the West Coast. And that website is already online, where you can connect with other building professionals of low carbon building materials, but also find all the necessary data for these materials. And because there are building codes for these materials, you can just go to the building code and see what are their prescriptive requirements. And of course, if you need to exceed those requirements and do something more interesting, there are many avenues like the Building Green Alliance that is online. There is also a lot of research that can be searched. So it is happening. It is still a junior happening. So there is a lot more to grow.
Great. We have a set of questions which have to do with cities and the urban. So I think I might ask them together. One is simply one question by another anonymous attendee says, asks about the juxtaposition of the rural materials, which this person calls rural, in the urban environment, and a kind of related question which says something like that, let's see, if we are, to the extent to which cities are being built with what this person calls lighter and transparent materials, there's a lighter transparency trend. So to what extent can earthen materials be used in cities? So on the one hand, someone is saying rural versus urban material, and then the first person is simply saying there's a trend to building glass towers with steel. How does an earthen material fit in that context?
Yeah, this is so funny, Lucia, because we had the same conversation about how sometimes architects really are drawn to lighter and materials that have allergy to these mass materials. And then I said that I have allergy to all these glass towers that I see, and I just think about how the heat and leaks out and gain and all the.
But it's true that there's a kind of, I guess what I was saying was that there's, and it's a modernist myth, of course, that there's an allergy to, in the sense that there's a fear of mass.
Mm-hmm.
Fear that the building will not so much be massive, but that it will look massive, that it will have mass in it. So I guess that's but your answer is that you have the opposite allergy, that you, your reaction to glass and steel.
And I have many examples of really inspiring earthen projects where you can find very minimal and elegant building details, just as you know, the aesthetics of concrete has its beauty as a mass, so does earthen materials that are more maybe sometimes rough, which is something that is really a matter of I would say aesthetic selection.
Mm-hmm.
And for me, the envelope system that is becoming increasingly thicker to allow different engagements with community, with food production, can today integrate mass in different ways. So it's not about having like an enclosure without any windows made of mass, of earth dome, as you can see in historical domes in Persian historical architecture with very small windows. That is, again, it's a bioclimatic architecture, but we can use these materials today in assemblies that are more light, that are more transparent, to achieve the advantages of earth. So it's a matter of decision.
Right. And actually, I now see that someone named Bisser Taba has asked specifically about the incorporation of earth and construction in urban building codes. Or is there something about the building codes in a city that would be sort of render earth and material construction difficult? And yeah, and I guess I could piggyback a third question onto that, just because it seems similar. This person says, if we need to have a steel structure to build up the concrete wall, then to build an earth material wall, there will require a different technique. So how does the assembly of these different techniques, let's say since you're talking very much, if I understand this question correctly, you're talking very much about incorporating these techniques into existing norms, including steel and concrete ones. What does that do to my building site? What does that do to the load calculations for having all this earth lifted up or not, for example?
Yeah, that's a great question. So first, for Bisher, thank you so much for your question, Bisher. There are constraints to urban development using earth and materials with earth and building codes, and it is now mainly limited to certain building height and to certain R values, of course, to account for the energy code requirements. So you have a certain thickness of walls. For instance, with straw bale construction, the R per inch is around R2. So you'll have eventually thicker walls than if you were using just a fiberglass bat. So those thicker envelopes then influence your building footprint. And this is one constraint that we need to overcome using innovative technologies. We need to find ways to enhance mixtures. We need to find ways to incorporate different modes of testing the soils or the fibers to have a more certainty about their performance. So this is a great question point. And the second thing was about Lucia, I can't remember now.
The construction site.
The construction site. That really depends on the type of earthen assembly chosen. By choosing, for instance, light straw clay, this type of assembly is highly compatible with mainstream construction. It's just that instead of the mainstream or the insulation material that is synthetic, you're placing a natural insulation infill. The weight distribution is not very different. However, if we are using load-bearing earthen construction, then there is that limited building height. So we not currently build a high rise from rammed earth. We're limited, if I'm not wrong, the highest rammed earth structure is 120 or 130 feet. So in order to incorporate earthen materials in high-rise construction, it is really about the infill, and it is about partitions. So internal partitions using clay-based partitions, the ones that I showed in my slide with the Levita partition, which is manufactured in Germany at the moment. And there are also different prefabricated panels made of light straw clay and straw bale construction that can be applied modularly. So these are some of the avenues that are happening now. But this is only one side, you know, there are so many exciting avenues to hempcrete, to fungi-based materials, to biomineralized concrete. Earthen materials is really for me an initial case study. I'm in love with earth, but it's really for me an initial dive. And what I'm doing now is really looking at the broader spectrum of natural building materials.
What an amazing mission statement. I'm in love with earth. In all senses of the term, fantastic. So I want to, we only basically have time to 2 more questions. The first one I wanted to report is that somebody's talked about the visualization. And of course, if your question's not answered, we can send them to Lola and she can kind of answer back. But if you put your name, if you don't, then you will not hear back. One person has asked that, has said that he or she appreciates your visualizations of the LCA results. Do you have any advice or recommendations about representing and communicating these type of complex information? And this is something you haven't talked very much about. What is your process like?
Yeah, what is the process like? So yeah, there were many visualizations, which are only a very few of the many that I have. And really the process is wow, this is hard to explain. I don't know. It's really about, I really want to to communicate the problem or the solution. And oftentimes what I really try to do is not only, not only show the problem, I'm really trying to convey the solution, to convey the path to solution. So I'm trying to, I'll call it positive visualization. So I'm trying to visualize as much as possible the possibilities and what I think should be done.
Great. Okay, so a kind of programmatic visualization almost.
Right. So it's like there will mostly be a path or like a story. And this is part of my work where when I was content developer at the Martech, it was really about storytelling, how to tell the story, how to, ask yourself, what is the nemesis that you're trying to overcome? But then what is then your path?
So were you using, this is my question, were you using flatten the curve before the latest iteration of flattening the curve, or is that a new post-COVID use of that term?
No, it's flattening the curve is also a carbon thing.
Carbon. Okay, so the last question we have come from our very own Andres Jaque, who says, I'll read the compliment as well. Thank you, Lola, for this excellent presentation of your work and research. It's a very important reorientation of the way technology is discussed in our sequence, and our sequence being how GSAPP teaches its architects in training. And Lola, you are going to be directing the technology sequence. And Andres says he's happy to see it builds bridges to discussions in studios and theory. Can you tell us more, and maybe we have a few minutes, about how you plan to engage with pedagogy? What's your teaching?
Yeah. Thank Andres. This is such a great opportunity to share that beyond teaching technological courses and on building technology, like 81 and 85 that I'm teaching this year. And of course, I will probably have a materials-based class. I'm also really keen to teach studio and, to be diving into design build. From the design process to actualizing the party diagram into something that is eventually built and influencing communities. This is something I'm tremendously passionate about, and something I would like to, I will hopefully do in my time here at GSAPP. And this is specifically for me, but for the tech sequence, it is really about keeping the building technology courses that are the core courses that are important and fundamental, but also adding a layer, maybe through the elective courses, this is still too early to know, of how building technology and what is the role of building technology in healthy buildings and resiliency. So in really, we have a choice. We're not driven necessarily by the industry. We need to choose where to direct our energy, and using building technology for the right purpose is really what I'm interested about, and not using it as solely as an instrument. And I think that the really exciting opportunity to intersect this with studio work and to equip students with tools so that they gain those tools and immediately implement them in their design explorations is something really powerful that we need to find a way to coordinate.
We can capture that design carbon in shorter life cycles, if I can afford myself a really cheesy metaphor. So Lola, I think that's it. I think it's my job. I'm reading the chat here. I think it's my job to close this out. Is that right? I think so. Thank you so much for the lecture and for specifically focusing on these materials, which I think need the good publicity that you're giving to them. And thank you to everyone for participating and for asking questions.
Thank you. Thank you very much.